Okay, well, let's begin. Um, so announcement-wise, we're getting pretty close to the end of the semester. This is class 37 that we have today, and we're only going through 41. So it's kind of remarkable if you think about it that way. We've got today's lecture, and then 1, 2, 3, 4 more. So we're definitely closing in on something. The project is due Friday of this week. Hopefully that's not a surprise to anybody. I feel like I've been driving that point home on a pretty regular basis since I assigned the project. So that project is due on Friday, and you need to turn it in before 11. And so I guess that means you've got 47 hours and 58 minutes to finish the project. And it's a big one. It's worth 15% of your grade. A couple of students recently have asked me questions that, they're a little bit more elegant than this, but essentially what they're asking is, what's the minimum I have to do for the project? And, I think the assignment description outlines the required elements of the project and, what sorts of things should be discussed in the report and what the spreadsheet could contain. But this isn't one of those situations where, all you need to get is the right answer. Like on an exam, no matter how sloppy your handwriting is or how circuitous and confusing your solution is, more or less, if you get the right answer, you get full credit for that problem. Well, that's an exam. The same isn't necessarily true on a big project like this. The grades are kind of more distributed along the lines of the quality of presentation, the clarity of the writing, the depth of the research. And it's not a discrete dividing line between yes, you did research and no, you didn't do research, because some students are going to have looked into a lot of different investment options, are going to now understand something that they didn't ever know about before, like index funds or compounding or fees on mutual funds. People are going to show varying levels of effort and varying levels of achievement, and the way that I grade is going to be holistic. And so it's tough for me to say, like, what's the bare minimum you need to do as far as like a page count or a number of references, because that's really not how this project is going to be evaluated. I'll certainly be looking at the spreadsheet, and it does need to be correct. If there are errors in the spreadsheet, like the way that you've set up your calculations, then you'll have deductions from that. But as with many things in life, it's hard to say, like, what's the least you can do to get by. So I would instead encourage you to think in terms of how can you show me how much you've done? Because I think probably most people in the class have really done a lot of work and have put serious thought into the project. And so, you've done all this work till now to figure things out. Now don't shortchange the opportunity you have to explain what you've done. You should invest a good amount of time in writing it up and making it clear and really showcasing all of the efforts that you've put into the project and putting together a report that you're proud of, that you could share with family members or look at someday in the future and not shake your head with disappointment, like I've done for some of the things that I wrote long ago. I have a handful of assignments that I'm still proud of to this day, and I hope that this will be that for you. All right, so that's your final pep talk on the project. It's due Friday at 11. Now, homework 14 is posted right now on Blackboard. You can get at that. That's the cost estimation assignment. It's due on Wednesday the 2nd, also before class that day. It includes some material that was covered on Monday. Now, like I mentioned already, Monday was kind of a disaster. If you joined Monday's class, you know it was a disaster. The screen sharing wasn't working, and so if I can't show you things, it's awfully hard to teach. I could just say it, but it doesn't have quite the same effect. I sent you a link to the lecture from last semester, and it's important for you to watch that lecture. That lecture has all the same information that I would have covered on Monday, including the examples and including the in-class exercise and indexing in particular. Cost indexes, those just have a habit of showing up on the final exam. So, at the end of today's class, I may have a minute to go back and offer to answer any questions that you maybe would have, but I can't cram 2 days of lecture into one class meeting. And so if you didn't already watch that YouTube video that I sent you the link for, you really need to watch it. It will come up. So Harry asked what was wrong with it. What was wrong with it? IT's not sure, but they verified and replicated the problem on their end, that they weren't able to share their screen either when I made them a presenter. So there's different rooms for each class meeting, and today's class meeting is a different room than Monday's was, and whatever setting was screwed up for Monday isn't screwed up for today. So that's good enough for me. Any questions on these announcements before we move forward? Not on the announcement slide, but on our schedule for the semester. There's a row-by-row schedule that I handed out along with the syllabus. Our final exam is Tuesday, December 8th at 10:15 a.m. So if you want to put that down in your appointment book, you'll be having your final exam on Tuesday, the 8th of December. That will be your last test, with me anyway. All right, let's talk about learning curves. Here is a picture of what's sometimes colloquially known as a sweatshop. It's people in a garment factory, and I don't know if you've ever seen a video of people working in a place like this, but it's just incredible how quickly they can sew shirts or pants. When I was in high school, we all had to take some sort of a home economics course, and you'd sew a pillow just so that you could see if you have any kind of needling skills whatsoever, and most of us didn't. But it made me appreciate how difficult it is to operate a sewing machine and sew things. And so if you've seen videos of people who've done this for a living for 10, 20, 30 years, people who've operated an industrial sewing machine, they can zoom through and do the inseam on a pair of pants in just a second or 2 seconds. And so the main point, the reason why I show you this picture, is to bring to the forefront of your mind the idea that the longer you do something, the better you get at it. You probably have noticed that same trend in your own life. Think about your hobbies and how quickly you can do something now compared to the first time you did it. Whether it's field dress a deer, or make a loaf of bread, or wash your car. Once you learn a few techniques and you know the order that you should do things in, you can get a lot quicker at it. Now, one of the ways that we quantify that experience is there's an equation that's going to tell you how quickly people improve. Because this whole unit of our course is about cost estimation and trying to figure out how much input is required to produce a certain output. So if you're a mechanical engineer working for Toyota and you want to know how many engines you can produce in a month, one of the factors you need to take into account is how well trained is the staff, and will they be getting better at their job the longer that they do it. So one of the inputs for that equation that I'm going to show you a little bit later is the K value. And K represents how long did it take the first time someone was exposed to the task. So let's just say, for instance, that this person, it's their first day on the job, and the very first shirt that she sewed took 12 minutes. So that would mean K is 12, and that's a baseline. What we assume is that people from there get progressively better. Now this is just a model, and I have to emphasize that models are useful, but they're not always perfect. A model could be like a physical thing that you build. Think about like a model airplane and what the purpose of that is. It's to represent a full-size prototype. So, like if you're building a little P-51 Lightning, then you get an idea of the wingspan relative to the size of the propellers and where the gun mounts were and how long the fuselage is. And so it's just kind of a representation or a simulation. Well, equations are also models. They simulate reality. And so the formula that I'm going to show you today, it's not to say that it's always perfect, but it's just one way of approximating how much time it takes to do things when you account for improvement and that learning curve of getting better the more experience you get. All right, so here's another look at an instance where experience counts and probably people get better. The longer they're on the job, they're able to put in the radiator more quickly, or assemble the brake pads and install them, or whatever the case may be. Automation has the ability to make things go a lot more quickly than they have in the past. And I've got kind of an interesting video to show you about automation and the future of where things are going. Let me just pause this recording for a second. What's kind of interesting is that rather than people going into the warehouse and picking things off the shelves, what these robots are doing is it's bringing the shelves to the people. And so the human operator who's actually gathering the items off of the shelves is stationary, and then the shelves just line up, and it's easier and faster and takes less people if the shelf comes to you rather than you coming to the shelf. And then they build the order, putting it into the buckets. Each item is scanned as it's coming off to make sure that the person has picked the right thing. And then what Amazon is able to do is, you'll notice that it's dissimilar items, that to save space, they don't have to necessarily keep all of the same things on the same shelf. You may have a toothbrush on the same shelf as a computer mouse. And there's no logical relationship between a toothbrush and a computer mouse other than just that's where the space was, and the computer has the ability to keep track of where things are. And the other kind of interesting thing that was shown a little bit earlier is how close together these shelves can get, because people don't need to go in the aisles. These little robots are going under and lifting up the shelving, and so you don't need a person-sized space, and that allows Amazon to reduce the amount of money that they're spending on warehouse space, because there's just a lot of empty space in an ordinary warehouse that these robots don't really require them to have. And so it's kind of interesting if you think about the future of automation and also the future of productivity. And so what we're trying to do today is look at ways to predict improvements to productivity. And what this model that we're going to be looking at can accommodate is both human improvement, but also machine-assisted improvement. And so I already told you in the previous slide about K. So K was the factor that defines how long it took the first time it was done. The next term that goes into this model, into this equation, is the ratio of doubling in productivity. And so what I mean by that, for instance, if someone is installing the oil pan and it took 40 seconds the 5th time that they installed the oil pan. So once you've done 5 oil pans, that's your total number of experience. What we're now looking for is how many oil pans does it take to double your experience. So if you go from 5 installed to 10 installed, you've now, during that increment, doubled the amount of experience you had, since 10 is twice 5. So what we do with this S factor, S is the ratio of input to double experience. And so if it was 37 seconds for the 10th oil pan and 40 seconds for the 5th, then what you can see is that it took 92.5% as much time once you've doubled your productivity. And so what we would assume is that then maybe this trend also continues, that when you go from the 10th to the 20th pan installed, that again, it only takes you 92.5% as much time to double your experience from the 10th to the 20th. Okay, so S is an important factor that goes into this model, and what you need to remember about S is it has to do with a doubling of experience. So here's what the learning curve looks like if we graph it out and look at things in a visual way. It's a model that is explaining productivity and also improvement in organization or maybe machine assistance. And what the idea is that if we measure at a couple of points on this curve, then we can extrapolate outward into the future. So if you're in the factory and you measure the first car that it takes to produce and how much time it took, and then you measure the second car and the 4th car, each one of those you've doubled your experience. You can kind of extrapolate that trend out into the future, and what you notice, this model assumes that the improvements are slowing down. You notice how that curve is getting flatter the longer we go? Why do you suppose that the curve would be getting flatter and not just continuing in a linear way? Anyone want to take a guess at explaining in the chat box or by unmuting your microphone, why is it that it has this particular shape? Like logically, if you think about things, the way things really work in the world, why is it that this curve is flattening? You can only do something so fast. That's right. You know, there are physical limits that you'll begin to bump up against. No matter how experienced you get, for example, you can't go from one end of the warehouse to the other instantaneously. There are real physical constraints like travel time or how quickly a drill spins. You know, like if I'm installing the oil pan, it's going to take me at least as long to install that oil pan as it takes to screw in. So if there's 10 screws and it takes me 3 seconds just because of how quickly my drill is moving, so that's 30 seconds just in the screwing, and that doesn't take into account also moving my hand from screw to screw. And so eventually I'll learn that repetitive motion and I'll be able to move more quickly, but there's a real physical limit. And so you can't get down to 0 time taken to produce something. Eventually you're going to bump up against that natural limit. So the other name for this besides a learning curve, sometimes it's also called an experience curve or a manufacturing progress function. And so here's the model. I told you it's an equation that simulates and summarizes reality. And so we already talked about K. K is how much time it took the first time you did it. Now, what we're trying to calculate with this formula is Z. And Z is how much time, or it can be input resources. It doesn't necessarily have to be time, because this same kind of equation could be used if you wanted to model like how much leftover scrap you have. Like if you're trying to minimize the scrap, and so it could be modeling wastage or something. But let's just think about this right now as time. So Z sub U just means how much time does it take to produce unit number U. So that could be, you know, if we're trying to figure out how much time it takes to put the oil pan on the 10th time. So then what that would be is you would find out the amount of oil, amount of time, the first one that you did, that's K. And now we've already talked about S. It is that decimal that says the percentage of time required once you've doubled your experience. And with S, you calculate N. And so N goes into this formula. It's an exponent that we use, the learning curve exponent, and then U is the output unit number. And so if we're doing the time required for the 10th oil pan, then we would use 10 as the U over on the right-hand side of the equation as well. So I think this formula will make the most sense to you once we go through an example together, and then I turn you loose on the in-class exercise. So let's look at an example. The case of sewing. If it takes you 85 minutes to sew your first pair of pants, so that's defining K. Okay, so if you're writing things down in the margin of your notes, K equals 85, or scratch paper. Now, it also tells us how much time it took for the second pair of pants and the fourth pair of pants. So sometimes you get more data than you need. And in this case, we can define S either by going from the first to the second pair of pants, because that is the doubling. To go from 1 unit to 2 units, you've doubled your experience. So we could calculate S from the first to the second, or we can calculate S from the second to the fourth. And what I'll illustrate to you is that this is consistent, that in this example, the way that I've set up the data, S is the same regardless of whether you go from the first to the second or from the second to the fourth. Now in the real world, there's also going to be kind of just like random variation thrown in there. You know, like maybe what if someone got startled or distracted as they were working on the fourth pair? So maybe it would take them a little bit more time. So if you've got multiple data points, what you could do is you could average the S for as many different data points as you've got in the real world. All right, so what we want to find out here is how long will it take to sew the 10th pair of pants, and then I'll just do a brief spreadsheet illustration to show how much time would it take to sew 10 pair of pants in total, including the first pair, the second pair, the third pair, and so on and so forth. All right, so what we need to do is just define these variables. K is 85, S is going to be 76.5 divided by 85, or S is 68.85 divided by 76.5. Either of those will give us S. Once we have S, calculate N. Now U, we want to know the 10th pair of pants, and so U is 10, and that's all that we need. So let me bring up the solution on the screen here. Oh, that's not it. Okay, so we're doing the learning curve here. K is 85 because that's our first pair of pants. And then the S is the ratio of doubling in experience. And so it's important that we know it's going to take you less time the more experience you get. And so this ratio S should be less than 1. If it's greater than 1, what that would imply is that you're getting worse over time. And you know, there is beginner's luck. But overall, the trend is that you're going to get better the more experience you get for just about everything. So don't make the mistake of accidentally inverting the time for the second and the time for the first. It should be such that you end up with an S value less than 1. So you can see if I did it with that data set, it's 0.9, or just to check, what's the S value if I do both the second and the fourth, which is again a doubling in experience but different time amounts. It was consistent. So the S value is 0.9. And if it had been a little different, maybe I'd take the average of the two and use that to calculate N. And that's where things are headed next, is I'm using the S value that was just computed to determine N with this function. So that was defined here on the slide. The log of S divided by the log of 2 is where you get the learning curve exponent. So our learning curve exponent is negative 0.1520. And it's a good practice to keep as much precision in your calculator as you can. You know, don't round off. Don't round this off to 0.2. Your data would get pretty sloppy. Keep all of the digits in your calculator and then round off at the very end. All right, so to find out the 10th pair of pants, that means U is 10. And here's our model. We're going to have the first pair of pants, K equals 85, and then 10 to the learning curve exponent of negative 0.1520. And so that means that to sew our 10th pair of pants would take 59.9 minutes. Okay. So are there any questions about that first part of the example? Now, the second part of the example asks for the cumulative time, the total time required to sew 10 pair of pants. And so to do that, we already know the first pair of pants, how long that took, and we know the second, but we need to know the third, here's the fourth, the fifth, sixth, seventh, eighth, ninth, and 10th, and then add it all up. So we could repeat this formula for U is, we have to do 3, 5, 6, 7, 8, 9. We can do it over and over again. Or we can automate it with Excel, which is nice to have the option. So let me just illustrate for you how we could put this equation into Excel. Start with the blank workbook, and what I'm going to do is I'm going to paste the formula that we use just so that we have that handy as a reference. So here's our equation that we're going to be using. All right, so S, which we calculated before, was 76.5 divided by 85. I already know it's 0.9, but let me just put it in here anyways. 76.5 divided by 85. Okay, so that's my S value. And then N, remember the formula for N is the log of S divided by the log of 2. So log of S divided by the log of 2. Okay? And now I'm going to have the pair number and then the time that it took for that pair of pants. So this formula is what we're going to use. So I want to know the 1st through the 10th, all 10 pairs of pants, how long did it take cumulatively for each of them? And the first one was 85 minutes. So what I can do is just apply this formula where the pair number, that is going to be our U, in other words. Okay, and then this ends up being our K, because that's how much it took the first time. So for the second pair of pants, we have K, so I'm going to reference this and lock the reference so that it's always 85, times U, which is this, to the power of N. And I need to lock that reference as well. And it says 76.5, and that's what we already knew to be the case. We already knew that the second pair was 76.5, so it's behaving normally so far. Let's also double check when we get to the fourth pair if it says 68.85. All right, so scroll down through all of these, 68.85, so that checks out. And then the total amount of time that it took would be now the sum of each of these individual times. So to do all 10 pair of pants, it's 679.5 minutes. So that's how we could do the cumulative time. This is the cumulative amount of time required to sew all 10 pair of pants. And we put that little statement in there just because it's a good idea to offer a conclusion and make the answer easy to find so that the grader doesn't have to go on a wild goose chase through your spreadsheet to know if you did it right. All right, any questions about that? Here's the one that I would like you to get some experience with. What if it's a Rubik's Cube? Probably you'll get better at that the more experience you have. So what we know is the following data. What we're trying to figure out is how long will it take you to solve that Rubik's Cube the 100th time that you go through it. So we have the 2nd, the 4th, the 8th. We don't know the 1st. So that's a little bit of a wrinkle because K, remember, is how much time it took the first time you did it. So before I pause and let you start calculating, has anybody got an idea of how we can solve this issue of the missing data for the first try? If we don't know how long it took the first try, what might we be able to do to estimate that?
I would just divide with number 2 in half.
Okay. So if we did number 2 in half, then that would say 12 minutes. I mean, that wouldn't really fit the pattern of what's going on, though, because it wouldn't be like that it took you 12 minutes the first time and then it took you 24 minutes the second time. So that's a fine starting point as a guess, but it wouldn't fit the trend of what we see is that it would have taken longer. So we know that try number 1 is going to take more than 24 minutes because that was our first time doing it, and we should be worse at it on our first opportunity than on the second.
So
Could you take a ratio?
What do you mean, a ratio?
Could you take a ratio between 2 and 4 and 4 and 6? to determine an S value,
Mm-hmm. And then what?
and then find your N value based upon log S divided by log 2.
I think you're right in the first part. We do want to determine S, but we won't necessarily need to calculate N from it, because at least not at first. What we want to do is we want to estimate how long did it take that first time. And so you said if you go from 2 to 4, you can get a ratio there. So from 2 to 4 represents a doubling of experience. And then the other doubling would be to go from 4 to 8. Not to 6, by the way. Going from 4 to 8 would be another doubling of experience. And so once we know S, what can we do? We can either go forward in time, or we can go backward in time and use that to estimate how long it took the first time. So even though we didn't measure it, if this is following that trend of S, we could use the S ratio that we got from 2 to 4. We could use that same S ratio to back calculate how much time it took the first time. You get what I'm saying?
Yeah, that makes sense.
Okay. So here's what I'm going to do. I'm going to stop talking for now and calculate S. And once you know S, either based on 2 to 4 or 4 to 8, use that ratio to find out how much time did it take the first time. So what is K is the first step. And then once you determine K, then you should be able to get N. And finally, Z sub U for the 100th time you solve it. All right. So I'll pause, give you some time to work, and then, of course, as we do, we'll rejoin in just a moment and go over the solution together. All right, well, let's go over the solution here. If somebody's stalled and not sure how to proceed, then additional time probably isn't going to help. All right, so the first thing we want to do, like I mentioned, is try and figure out, synthesize, how much time did it take during that first try. And so we can back calculate it by, first of all, determining the doubling ratio S. So it's 91% for this, which means that when you go double your experience, that now it only takes you 91% as much time as it did when you had the previous amount of experience. So to go from 2 to 4, for example, or 4 to 8. So I've done that. I've checked to make sure that it's consistent between both of the data points that we've got, and it is. And just because I had the S value, I went ahead and calculated N to have that at the ready. But to determine how much it took during the first time, then it would be the second time divided by S gives you the first time. So let's double check to see if that's the case. So what we should know is when we go from 1 to 2, that it only takes 91% as much time in the second time that we do it. And so it would be 24 minutes divided by 26.38, and that is 90.978. So yes, that's 91%. All right, so now we know K and we know N, and we can substitute it in for U equals 100, meaning that we want to know how long will it take you to do the Rubik's Cube on your 100th try. How good are you going to physically be able to get? And if you follow this same learning curve, and you're not picking up some hack, like there are, I think, like algorithms where if you follow a certain pattern, you can solve it much more quickly. But in this case, if you just follow that same learning curve function, then after 100 tries, it will take you 14.09 minutes. Okay. So that's learning curves. Any question about that example? All right, now the key thing that I said, you really need to go back and watch the video from Monday. If you didn't already, you really should go through the in-class exercise and not refresh, you should learn this cost index stuff. And what a cost index allows you to do is look at how prices vary over time, because there are these databases that give you an idea for overall how prices have changed between two different time periods. And that index can be used to find the specific estimate of an item's cost in the future. And so if you know, for example, that housing overall, that the cost of a house has, back in a certain previous time, had one price, and overall nowadays has another, you can use that benchmark data to calculate the index. And then if you know the previous specific price for that item, you can now calculate the price in a future date. So this is a really powerful idea that we'll combine in a future in-class exercise along with some other components. But it inevitably shows up on the final exam. And so if you didn't already watch that video from Monday, I'd encourage you to go through the in-class exercise and be sure and watch that information. All right, so remember the announcements. The project is due now in 47 hours and 14 minutes. And homework 14 will be due on Wednesday, the 2nd of December. So that's it for today. Hope you have a good one. I'll see you in class on Friday, and when I do, you'll have this big feeling of relief because you will have already submitted your project and you just feel like the weight of the world is off your shoulders. All right, that's it. Take care, everybody.